Good afternoon to all. Myself, Anil Kumar, and I'm here to start the second lecture in machine learning and its application course, which I started yesterday, which is basically as a journey from machine learning to deep learning for remote sensing image processing. Here you see in the second lecture, the title we have kept Journey of Classifiers from model based to data driven. So in this lecture you will see the very basic algorithms which were there for classification, and today we have reached to very advanced algorithms in machine learning, and further sub title we have within that deep learning algorithms for different applications. It can be for classification, prediction, or it can be for detection purpose, and further we can use the detection application within classifier. There is models in deep learning for segmentation. There are models for image transforming from one image to another image. So why you want to attend this course? That is the first question it may be coming in your mind, which is basically a 5-day course. Here basically what you will see, you will try to understand what is machine learning algorithms, and you can apply in your area, and some of the case studies we'll be talking about during these lectures. It can be mainly on agriculture, then on disaster, then urban areas, and you can have some specific applications. So here you can see for a specific crop stage mapping, any stage of the crop, can we map that field? Then can we have application in crop insurance? Can we have application in specific vegetation mapping within forest or within agriculture specific crop? Can we map a specific crop which has been affected due to disease or which has been affected due to flood? So then we can have post damage mapping. It can be due to earthquake, some activity has been occurred, and due to which some area has been affected and some damage has been occurred. Then map a transformed class with time. So secondly, in urban, we can see in a given time frame of say 6 years or 5 years, a particular class has been changed. For example, a very common change phenomena we can see in urban, the open space, which can be a land without grass or with grass, has been converted to urban, and in urban means building. So that transition can be mapped, which has been occurred in a given city in the last 6 years. So all these applications you will see during these lectures. Coming to very basic term due to which machine learning and deep learning algorithms has been developed with time is the pattern recognition. So here we'll try to understand the basic attributes of humans on which basically this pattern recognition works. So when we try to recognize an object, we try to see the features of an object. The feature can be color, its shape, size, association, shadow, and so forth. Maybe we can incorporate regions. In a region, a common object is there. We can also see the shadow, the 3D effect, and a neighbor effect, and so forth. So here in pattern recognition, narrow application, you can have object classification, like direct application of human perception. What we see through our eyes and then we perceive, right? Same way can the algorithm can do as an object classification. Other applications we can have for pattern recognition, like for prediction in stock market, or nowadays you can see on your smartphone the weather prediction. Every hour basis you can see can the weather be predicted, and can you see after 1 hour the rain will occur or not. Then we can predict the control on the vehicles, in the chemical plants, and so forth. So broad application we can see for classification or for prediction. These are the two applications in machine learning. But the moment you go to deep learning, you can have further applications for image transformation, changing image from one type to another type, then detecting the objects, and further this detecting approach we can apply in the machine learning so that we can improve our output results. Basic requirements for inferring the object to feel about an object. So here you can see the object as a small baby, and here we require a source of light which is falling on that object. So object with unique signature, you can find out the soft skin of a baby, right? They don't speak much, they give expressions, and quite unique expressions. And then the somebody, if it is looking them, that look works as a sensor to capture the signature of that baby. Signature means the different features, and then receiving through our mainly the eyes, the maximum information content is going through eyes, and then in the brain we can do interpretation. So this is the way, the basic feeling of an object we can have. About an object. And then you can see here identifying this famous person. Initially we don't have much clue, only small face and some portion of the shoulder we can see, and we get lost because clue is very less. That means training or ground truth information about the object is very less. The moment when the ground truth information or the reference information is very less, or the training data is very less, the algorithm has more confusion, more uncertainty to predict or to classify or to guess what this object is. Same way here, just again seeing some small portion of the face, it may not be possible. You can try with your own photograph. If you just see small portion, maybe you yourself cannot recognize. So that is the way the algorithm fails. The human beings fails when they don't get the full information about the object. So here you can see some further information and further. So more the information we see about the object, more easily we can recognize. So this information helps to train the brain. Same way when we are using machine learning, the machine learning algorithms get trained using the ground truth data or the reference data. They can predict the output more nicely. So here it can be say the conclusion is George Bush wearing a turban, and here basically we can identification nearly instant once we get the right facial feature for the person. So that means if we get the reference data, we get very high accuracy for recognizing an object or to classify an object or to predict the label of an object or the event will occur or not. So here inference, extracting the right feature plays a crucial role in successful classification or recognition. So this is very, very important. Once we have the proper training, once the human being is trained for a particular task, when the creature is trained for a particular task, they can do that activity very nicely. Same way here, if the algorithm is trained with a given training data, the algorithm can give very high accuracy for classification or for detection or for recognition purpose. So that is more important. And here you can see for extraction about an object, the step one is extraction. Have a digital image of collection of fruits. Then basically objective, once we have the collection of fruits as an input data here. The objective is to classify each piece of fruit. So here the objective is we want to classify each piece of the fruit. What is this fruit, what is this fruit, and what is this fruit? How do we start this exercise? That is a question mark. So this is a problem. So here you can see how this recognition approach works. So some unique attributes of fruits will help. So once we have very unique attributes of each fruit through training samples, and from the training samples we can extract the uniqueness of the fruits as an attributes, that becomes easy to recognize that fruit. It can be for like mango, so we know it is a green color or yellow color, and we know its shape. It's very prominent shape of a mango in India. It can be watermelon, again, the shape from outside and the material inside it is present. If it is cut outside, how it is there, its shape of watermelon. So all these are the features which are unique, which may not be similar to other objects, and with these features we can easily label the input data as per classification, or we can do prediction. So here, what attributes or features to choose? So that is a big question mark. If you are processing image or any other data, the question is what attributes or features to be extracted from a given training data. So here you can see for these fruit example, for apple and other these fruits, the color we can pick, shape and weight, right? So pineapple is having more weight compared to other fruits in this case. Color is unique sometimes, it can be same also, but we can see other parameters also. So here you can see the feature measurements form the feature vector. So once we have the feature of each object, it can be color, it can be shape, it can be weight. So this vector is your feature vector of an object, and objects form the class vector. So then once we have this feature vector, we can frame the class vector. In each class, their features are stored, and we can have the each object as a class vector. The simple classification problem, now we can try to understand how this can be done. Again, with a case of a bunch of fruits, if we have to simplify, consider only apple and pears. So we are just trying to classify two fruits, apple and pears. From a collection of apples and pears, measure the features. Suppose first is color and second is roundness of each piece of fruit. That means its shape, which is in the form of round shape. The measurements will represent typical fruit according to the measurement data what we get for apple and pears. For color and roundness, we may get a unique signature or unique type of these parameters, which can be called as signature of that fruit. So plot data on a two-dimensional plane, one dimension for each measurement. So here we have measured two parameters. One is color and roundness. So we can plot this data on a two-dimensional plane, which is called feature space. Right? In feature space, we plot the features extracted from a given data. In an image, if we have RGB, 3 bands, so if we plot all the 3 bands on each one axis, so that complete space is your feature space, and on that you can see the pixels of the images has been plotted using the color value from each band or each layer. So here you can see on the x-axis the roundness or not roundness has been plotted, and here the color has been plotted. So then we can see if it is pears shape or apple, both are more or less in this feature space has been plotted, and you can see very easily that we can have a separation line which can separate, right? And this complete graph is called feature space because each axis is carrying the feature. And here, if you see this one, this is a feature vector, this is a feature vector, this is also a feature vector. So whatever points we have plotted, they are feature vector in the feature space. So numeric value we have given, roundness we have given suppose 0 to 1, and for color we have given some value 0 to 1, so that easily on the same scale both can be accommodated. So here you can see the hyperplane. So through that you can separate the apple with pears. Even though color is different, roundness or shape is different, still we can separate through this hyperplane. So this is a decision boundary to make two classes from a given two bunch of fruits. So here once from this approach, once we are able to draw this hyperline, that means algorithm is trained to draw the separator or decision line. And here you can see between two classes of apples and pears, we can easily draw the decision rule. So once we get a unknown object, that means unknown fruit, and we want to label it. So here this is an unknown fruit or object, we want to label it, it belongs to which class. So here in this graphical display you can see this point comes in the area of class 2, so we can easily label this fruit as belongs to class 2. That means that was apple in the previous diagram. Further we can see in this feature space, it is more easily we can see this effect, that is our class is linear or non-linear boundaries. So here you can see the two classes C1 and C2. When you plot in the feature space, you can easily draw a decision rule, decision line or hyperline or hyperplane. So here, since it is straight line, that indicates here the classes are linear, and here if you see the same two classes, you cannot draw a straight line, you have to draw some curve. That means here it is a non-linear function. Here it is a linear function. So non-linear separation between two classes is not easy to handle. We have to apply some techniques, and we will see later how to handle this non-linear boundaries between two classes. And this problem of non-linearity we found in the remote sensing images also. So there we have to be very much careful to handle this non-linearity between two classes. So you can have the this feature space 3 in the 3D mode, where we can plot the hyperplane. So here you have first feature on the x-axis, second on the y, and third on the z. So again, these are the two classes, green one and the red one. So we can draw a hyperplane which can separate these two classes in three-dimensional feature space. So here you can see feature space. Then the decision boundary is n-1. So here you can see this hyperplane is two-dimensional, which can be plotted, and we can separate these two classes. So dimensionality in the feature space depends upon the dimensionality of the data. In the case of image, if you have a remote sensing image of 5 band, and if you are using all the 5 bands, your data will have, or the feature space will be of 5 dimension, 5D. Physically, you can have maximum 3D, but mathematically, you can have n number of feature space dimension. Dimension of feature space can be n, right? Depending upon dimensionality of the input data. Next is we can try to understand between two jargon words. One is recognition, second is classification. So here, if we see an example of faculties in a university as like professor, assistant professor, or professor emeritus. So here we can just classify the 3 points which are basically professors. So we are just grouping the people having the common property of professor. So these points are basically as professor, and this is a problem of classification. So classification means learn to match a form of learning and a process of grouping objects together into classes according to their perceived likeliness or matching. They're matching 100% or 99%. With that accuracy, we can group the objects having similar properties or similar features, and this basically classification problem. Learn to match. In recognition, if you see, the recognition means if there is a text here which is incomplete, still algorithm recognizes what is this text is. So what is it? It is basically cat and thee. So these are the words present in a given text which can be recognized, and this is the input, and here we are getting the output. So here it is a recognizer or recognition problem. It is trying to recognize what is there in the input data. So recognition means learn to reason, and there it was learn to classify. So here learn to reason, a form of reasoning and a process of applying rules and relationships to deduce decisions. So the recognition algorithms has a good application to make completeness in the input data. If the data is not complete, so we can use recognition approach to make the data complete. Then categories of classification, if we see, first is unsupervised, or also called self-organized training. Self-organized, that means that the algorithm itself organized to train. Train means to calculate the parameters of the algorithm to require to start the algorithm, right? So it assumes initially, and with the help of iterations, it adjusts the assumed values which are required, which are the initial parameters to start the algorithm to classify or to predict or to detect. So, but it is unsupervised. That means there is no training data is given, or no reference data is given. So algorithm has just input data, and the algorithm requires some parameter to be initialized. So since there is no ground truth data, there is no training data, so algorithm, what it does, it assumes the parameters, and it has some iteration provision to be given 10, 20, 30, 40, 100 times. So it iterates, and through that iteration, it refines the parameters. Once the parameters have maximum refined, it stops the refinement doing the to the parameters, and then it classifies the data. That's called basically clustering approach. So unsupervised algorithms are also called clustering approach. Second approach of learning is supervised learning. It is like in a class. Here in a class, when there is no teacher, still students are learning, so it is unsupervised class. Supervised class is supervised training, or supervised class is teacher signal is known. That means there is a teacher present in the class which is teaching to the students. So with the help of teacher, students are learning. So whatever teacher says, they accept as it is. So in supervised learning, there is no iteration provision. In a single iteration or a single step, they understand about the topic. So here you can see the self-organized algorithm or unsupervised algorithm, how it works. The simplest algorithm what has been chosen is k-means. Simplest means the algorithm which are designed to work as unsupervised, then their initial parameters should be simple in nature, like k-means. K-means means k means number of clusters. Means it is working on a mean parameter only. So mean is easy to refine. So initially for this given input data, we have to divide this data into two classes. So initially it assumes the two mean values for each cluster, and which is quite out. And with respect to iterations, it is trying to define them. After few iterations, you can see mean has been shifted here. After few iterations, mean is here. And after few iterations, mean is here. And after, say, this is a fourth iteration going on. And after fifth iteration, it found the one mean is here and one mean is here. So you can see with number of iterations, initially mean was assumed. So this was the assumed value here. but with iteration these means are refined, and finally it is found that mean should be somewhere here for cluster 1, and for cluster 2 mean should be somewhere here. Here you can see we can do it for more number of classes. Initially I've given you example of 2 class. We can start with 3 class, 4 or 5 clusters, not class. In unsupervised we use the term clusters, so we can have 2 cluster approach, 3 cluster approach, 4 cluster approach, and 5 cluster approach. Here there is one rule called elbow point. Elbow point means when to stop. Here we are starting to extract how many clusters from 2 to 5 we have reached. The question comes, how many large number of clusters we can extract from a given data. So that is an elbow point. So here if you see through this graph, the number of clusters are more or less getting saturated, more or less tending to infinity. At that point we can stop to extract number of clusters. The advantage of self-organized training or unsupervised algorithm is the application of this algorithm is it is applied to a data where we do not know about the ground, and we can try to know how many number of classes are present in a given data. That means from a given image how many number of clusters we can extract, and that also conclude that how many maximum number of classes are present on the ground. So that is the only application of unsupervised. Of course we have to do unsupervised when we do not have training data or ground truth data to train the algorithm. I hope my video and sound is going fine. If okay, so we can move further. In between you can see some lines. So coming to next is supervised learning. So here in this approach we are providing some extra data as training data to the algorithm. So here you can see this is the input data, this is output, but here in between we are providing the teacher signal, that's the training data or ground truth data, right? So based on this data, algorithm get trained. The parameters what we are trying to refine in unsupervised approach, here we can directly calculate these parameters from a given ground truth data or training data, and plus the labels also, right? Because that the label is also present. So then once the algorithm is trained from the training data, we can use it, this trained algorithm, for all unknown samples to classify or to predict as an output from the algorithm, and they will have the labels. Here we can see more about little say remote sensing linkages with supervised and unsupervised approach. This is a remote sensing image, say B1 to BK band data. So this is the image form. Each band is in the form of matrix, and at each pixel location you may get k number of pixels from 1 to k, and here it is going in the algorithm. But we have ground truth data for 4 classes: water, forest, urban, and sand, called teacher signals or training data, which is used here to get the features. So using these features we can have a matching, and we can classify in each pixel which class is present. So here it talks about this is forest, this is urban, U, W is water, S is settlement, and U is again urban, F is your forest. So this way we can have thematic map in single iteration because it is supervised approach. Very basic algorithm you can see for supervised. A typical teacher signal approach is MXL, or maximum likelihood classifier, which is having the training data defines the statistical parameter of the statistical distribution, probability of an unknown pixel being one of the class, and if an unknown pixel has brightness value within the weighted region, it has a high probability of being as wetland. So once since in MXL it works on probability based, so if we have the training data, we can find out the probability of each class, and once we have unknown pixel, we can find out its probability for each class using the training data for a class. If it is maximum, so that unknown pixel is labeled to that class. So here you can see the maximum likelihood classifier. Here, if we are trying to map a forest pixel, and if the probability is greater for forest than for agriculture, so that pixel will be labeled to forest, because probability of forest is more for a given X. And you can see here the case of minimum distance classification for agriculture using Mahalanobis distance. Here you can see the given satellite image as an original input image, and this has been classified with labels. So here you can see this has been picked up as water, dark blue, gray color is your settlement. Then here this is grass. Then this is your forest patches here. There is some shadow also, cloud also, but cloud and shadow is not a class, but that is just an effect which can be minimized, and so forth. Some of the drawbacks, if you see, drawbacks of statistical method. So whatever previously, if you see, there was no word called machine learning. Previously, some classifiers are under the category of statistical methods, like your C-means, then parallelopiped or called box classifier, or MLC, maximum likelihood classifier. So these are the very basic algorithms which was developed, and they are basically under the category of statistical classifier, because they were using statistical parameters, your mean, variance, covariance, standard deviation, minimum, maximum, and so forth. So they were statistical methods, and if you see and study these algorithms from the literature, you will find some limitation or drawbacks of these algorithms. One, like for MLC, it follows an assumption of normal distribution function of objects' gray levels. They were pixel-based algorithms. They are using the pixel information, no any other information. Pixel information is basically as a color information the algorithms were using. So if you talk about MLC, maximum likelihood, which was a statistical algorithm, it has an assumption that all the input data should be normally distributed function of objects using the gray levels. Secondly, works largely well for images of resolution of about greater than 10 meter. So if you have images medium coarser to coarser pixel size, these algorithms will work fine, because they are using only the color information. Finer resolution data, like nowadays you have 1 meter pixel size image, or less than a meter, 0.5, 0.4, 0.3 pixel size image is available. So that is very finer or very high resolution image data. How to process will have other interpretation parameters. So these images cannot be classified with these basic statistical classifiers which are using only color. And if you try to do that, the leading to classification error will be unacceptable for many applications, because in high or very high resolution image of say pixel size 0.3, 0.4, 0.5, and if you're trying to map buildings or built up area, there you can see individual object is dominating. There can be dominating of roads, dominating of buildings, residential building or industrial buildings, some structures in the lawn or parking or areas, or in the your different parks. That can be some small structures, they will be dominating. So it is not just easy to map them or classify them using their color information. We have to use some other interpretation parameters. If we just use the color, there will be very high classification errors, and which may not be acceptable. So terms in classification jargon. So as I've mentioned about these statistical, nowadays we talk about machine learning. There are large number of algorithms. They were categorized in different forms. Some were statistical algorithms, some are fuzzy based algorithm, some are linear mixture models, some are decision tree based, right? Some are statistical learning algorithm like support vector machine. Nowadays, all these algorithms comes under one umbrella that is called machine learning. So there is no very region-wise division of these algorithms, maybe with respect to properties like statistical algorithm, fuzzy-based algorithm, decision tree algorithm, statistical learning algorithm like support vector machine and so forth. Today, you have one common umbrella of machine learning under which all these algorithms comes. Some terms we can see in the classification jargon, like parametric algorithms. Parametric means they are based upon statistical parameters like mean, standard deviation, variance, covariance, minimum, and maximum. So these are the few statistical parameters. Based on these, the statistical algorithm works, and they also call parametric algorithm. Parametric algorithm means you are not worried to optimize the parameters of the algorithm. It is just like A into B, right? Anytime you multiply two numbers, it will give you exactly the same output. 2 into 3, you multiply number of times, you get the same output. But there are non-parametric algorithms also, which does not work directly with the given input. So they give different output for given input. But in the parametric, you apply different number of times, you get the same output. That's the meaning of parametric. You don't have to optimize the algorithm with respect to different parameters. So parameters are directly calculated from the given input data. But there are non-parametric algorithms which learns from objects or from the given input data to decide of to generate polygons in feature space, basically to create different classes. So there are non-parametric algorithms. That means their parameters are not standard. They have to be optimized every time. It can be fuzzy based algorithm. It has some extra parameters or weight constant which has to be optimized. There are learning algorithms like ANN and further algorithms under learning domain. In that there are so many parameters like learning rate, momentum. All these parameters has to be optimized. Always, we cannot take them straight for classification, and that's why these algorithms comes under non-parametric range. Non-parametric means the parameters are not straight calculated from the data. We have to optimize their parameters. Then type of classifiers we can see with different categories. Pixel-based classifiers, which are using color information of a given image. The machine learning algorithms are generally designed to use color, and they are basically pixel-based classifiers. But we can take more parameters from the image, not in place of color. We can take shape, texture, size, hierarchy, association, through segmentation, so forth. So then when there is more than one parameter we are using from the image, then it is called object-based classification. The commercial tool for object-based, very dedicated tool developed in 1999 was Ecognition software, and nowadays there are so many tools available. In ADAS also you have a tool available as an object-based. Coming to statistical algorithms, which are using statistical parameter and which are also pixel-based parameter and which are also parametric algorithm, like k-means. K is a number of clusters. It was designed unsupervised initially, but nowadays we can use this supervised also. Then MLC, maximum likelihood classifier. It can have three norms: equilibrium distance norm, Malroney's distance, and variance, diagonal variance covariance norm. Box classifier or parallelepiped classifier, fuzzy classifiers. So these are all your statistical based algorithms, and there are so many other. Then you can have learning based algorithms like ANN, RN, CNN, RNN, and etc. There are so many algorithms under learning domain. Learning domain means the algorithm which are using weights. So that algorithm is called learning algorithm. The algorithm which are using statistical parameter, that's called statistical algorithm. Statistical learning based algorithm you can have like support vector machine, because it uses variance, it uses statistical parameter as well as weights. So this comes under the category of statistical learning based algorithm. It has two flavors, statistical and learning. So statistical parameter plus weights is also used. Then you can have decision tree concept algorithms like DT. So where we can have some rule based classifiers. These are called decision tree. Then you have random forest, cart, and so forth. They are modified versions of decision tree. But basic algorithm for rule based classifiers is decision tree. Nowadays you can have random forest, you can have cart, and so forth. Then further, all these algorithms today can be used as a hard classifier or soft classifier. So question comes when to use hard and when to use soft. When we have pure pixel, that means in my image all pixels are pure. That means all pixels, each pixel has only one class, so it is a pure pixel. So we can use hard classification, which will label the pixel as 0 or 1. It uses the crisp set theory. But once we know in my pixel, it is a mixed pixel, that means there is a class of forest, there is a class of water, and there is a class of settlement, 3 classes. So it is a mixed pixel, which cannot be handled through hard classification. If you apply hard classification, some of the class will be overshoot and overestimated, and some of the class will be underestimated. So in that case, we have to go for soft classification using fuzzy logic concept as a fraction images we can get. And this soft approach comes from soft computing. So this can extract these classes in the form of membership value mu, and this can represent forest is 0.3, water is 0.3, and settlement is 0.4. Summation can be 1 or summation may not be 1. It depends upon algorithm to algorithm. So today you can see this line very important. Any classifier can work as hard or soft. So there is no limit. Some algorithms are already designed to work as hard or soft, but during implementation we can modify all the algorithms we can use as a soft classifier, and we can also vice versa, we can convert them as a hard classifier. So today there is no limit, and there is a very good example you can see in the commercial scientific tool NV. Whatever classification algorithm there you see, you can get the output as soft and hard. So that concludes today. You can use any algorithm as soft, and same algorithm you can use for hard classification depending upon in the image or your data has how much uncertainty. If there are pure pixels, so there is no uncertainty. If there are mixed pixels, partially or fully, then there is very high uncertainty. That cannot be handled through hard classifier. You have to go for a soft approach. Basic to latest classifiers, if you see, it has been listed here. Basic classifier, the very first one was C-means or K-means, then box classifier. This is also called Palopite classifier. Then maximum likelihood classifier. Then you have very popular nowadays when you try to attend machine learning, artificial intelligence courses, they talk about that they will cover decision tree classifiers, random forest, classification, and regression tree, CART. So these are the decision tree algorithms. They think this is the only algorithms which are used in machine learning. No. Today, any algorithm you can see which is listed here can be used for machine learning. So it is not only this one, but generally, if you see in the commercial programs of AI and machine learning, they talk about only the decision tree or support vector machine classifiers. Nevertheless, you can see more listed algorithm here. You can have fuzzy based classifiers, very good range, starting from fuzzy C-means, possibilistic C-mean, noise clustering, improved possibilistic C-mean, modified possibilistic C-mean. Then there were some algorithms designed for hyperspectral data classification, but that is not only the limit to process hyperspectral. We can apply for multispectral also, SAM, spectral angle mapper, linear mixture model, non-linear mixture model. So this linear mixture model was applied when there was a term floated in 1999, subpixel classification. So subpixel was a very common term, but nowadays that subpixel concept has been diluted, and today you see dominating word called soft classification, because that includes all the algorithms which can be used as soft output. Then you come to learning algorithm. The very advanced algorithm previously was ANN, artificial neural network, but today with the concept of deep learning, this ANN has become as a base algorithm, and further you can see advanced algorithm CNN, RNN with deep learning concepts. Then you can have object-based classifiers which can use so many parameters from a given image, starting with color, shape, texture, hierarchy, segmentation, and so forth. So it is using more than one parameter, then your classifier becomes object-based classifier. And you can see all these algorithms can be used as supervised or unsupervised. There's one. Within that, you can use them hard or soft. Supervised and unsupervised depends. If the parameter of the algorithm is simpler, they can use for unsupervised. If the parameters are complicated mathematically, then they can use only for supervised, not for unsupervised. But all these algorithms within supervised and unsupervised, you can use them hard or soft depending upon how much uncertainty present in your data. If there is no uncertainty, you can use it for hard classification. If there is uncertainty in the form of mixed pixels, you can use it through soft classification. I hope my PPT and voice is coming fine. Presently, I can't get the feedback, but just I'm giving a break. If there are some, you can type your queries. Otherwise, I'll continue. And I go on putting some lines, choice, yours, life ones, birth ones, and death ones. Choose or have a good choice. And this is all about today's my lecture. And last year, in the first wave of COVID, we were able to finish our first book, Fuzzy Machine Learning Algorithms for Remote Sensing Image Classification, under CRC Press, Taylor and Francis. And this is available digitally on different portals, or hard copy of this book is also available. This is a very nice book where we have shared our own experiences, mainly for fuzzy-based algorithms for agriculture, forest, urban, earthquake, post-damage assessment, and so forth. And you can get a full range of fuzzy classifiers in this book.